So our next invited speaker is Eduardo Gabrielli. He is a PhD student at the University of Rome. He's going to talk to us about his new methods, his novel techniques that help us deal with quite a serious problem in the domain of federated learning, and that is how do we cope with poisoning attacks. And so, yeah, I saw this paper, looked really interesting, and I really wanted to have Eduardo on to talk about his research and share what he's discovered. So, over to you. Thank you for joining us today.
Hello, everyone. Thanks for the introduction and thanks for the invitation. So let me share my screen. Okay, so today I'll present our work that is currently under review at SAT-ML, that is a conference about security and machine learning. And this is a joint effort of my advisor, Gabriele Tolomei, from La Sapienza University, along with Dimitri Belli and Vittorio Miori from the National Research Council. And so in this work, we basically tackled the problem of protecting the global model from model poisoning attacks by exploiting the history of local models sent by clients. So I'm assuming that you are all familiar with the basics of federated learning, and let me jump straight to the core of our work by giving a brief definition of what model poisoning attacks are. And they are basically attacks that occur when the adversary manipulates the model's parameters to cause it to behave in an undesirable way. And so, of course, there exist several aggregation functions that try to defend against these attacks, like, for example, cram, boolean, and others. But as the research advances, other scholars, of course, find vulnerabilities, making them ineffective. And also, they are always designed to work up to 50% of malicious clients. And we would like to drop this assumption and work on the most general cases possible. Okay, so these are some examples of this kind of attacks. So all of them employ a different strategy. There is the simplest attack, the Gaussian one that just generates a perturbation vector randomly, up to more advanced ones like lie, that, for example, exploit the variance of the parameters to hide among legitimate local models. And then there are even more advanced attacks that frame the problem as an optimization task, like as you see, OPT and AGR-MM. And so, in any case, here you can see our threat model that is kind of standard, but for two details. The first one is that the attacker randomly selects B clients to compromise from the whole pool of participants at each round. So the identity of the compromised clients is always different. And the second one, as I said earlier, is that we go beyond the 50% threshold of malicious clients. So we experiment to up to 80%. Also, the adversary has full knowledge of the parameters sent by each client. And this is very punishing for the defense side, of course. And so our research bases on this question, that is, are maliciously crafted models less predictable than the legitimate ones? Or in the same way, are legitimate models learned with standard stochastic gradient descent or ADAM or others more predictable than models that are modified afterward by a model poisoning attack? And the answer is yes, because in this plot, you see an analysis on the time-delayed model information between consecutive models sent by legitimate clients versus 4 types of poisoning models. And the TDMI, loosely speaking, is the amount of information shared by 2 distributions belonging to different timestamps. And so by comparing the distribution of parameters of one model at time t and the same distribution at time t plus 1, so it actually changed in the meantime, we can compute the modal information, and we take the average across all the t rounds, like with a sort of a sliding window of size 2. And yeah. So as you see from the plot, the legitimate model, which is the blue line, is not perfectly predictable, but definitely more predictable than the malicious ones. And so the solution at this point, it's pretty clear, I hope. If we can estimate the local model of each client at time t by using the one at time t minus 1, we can compare the prediction against the actual local model sent by either a legitimate or malicious client and compute a sort of anomaly score. And this is exactly what Flanders does in a nutshell. So a bit more schematically, we start off by collecting all local models at round t, and we organize them side by side in a matrix theta t, so that each parameter vector sent by each client is a column of this matrix. And if we stack these matrices that we receive at each round, we get a tensor that represents the temporal evolution of each parameter sent by each client. And next, by using a sliding window, we slice the tensor down to a certain point in the past, and we feed this into a Mar forecasting model that makes an estimation of the next model sent by each client. And so at this point, we compute the, actually, we compare the column-wise, we compare column-wise the ground truth theta t with the estimation of Mar by using a certain distance function to get an anomaly score vector. In this case, we used the Euclidean distance. And so with this anomaly score vector, we have a measure of how much the estimation of Mar deviate from the ground truth, right? And so basically, if our previous analysis about the TDMY I was correct, the malicious models will have larger anomaly scores compared to the legitimate ones. And so at this point, we can filter out the models with larger anomaly score and aggregate the remaining ones with whatever aggregation function that we like. And so just let me say a couple of words about Mar really briefly. So it is a matrix autoregressive model that defines the matrix at time t as the combination of the matrix observed at time t minus 1 combined with two matrices A and B, the coefficient matrices, plus there is a white noise matrix called E that models the error. And so this is quite a simple definition, I believe, but not however that this is a Mar model of order 1. We chose to not use larger orders because we observed that larger correlations between consecutive models. So yeah, the larger correlation is between the models at time t and the models at time t minus 1. Anyway, of course, we have to find the best matrices A and B to get an estimation. And we do that by minimizing the error between the ground truth and the estimation for each sample in the sliding window. And we do that by using the alternating least squares. So we first optimize for A and then for B on the closed form solution of this equation. And now, talking about the experiments, we test Flanders on 4 different datasets that you probably know, distributed in a non-IID fashion with the Dirichlet distribution, and against our main competitor, FL detector, that is a pre-aggregation filter like Flanders. Then we measure the improvement of the global model accuracy when classical aggregation methods are paired with Flanders as a pre-aggregation filter. And ultimately, we assess the performance of an adaptive attack based on MAR. And as you see on the table on the right, there are a bunch of hyperparameters. So we use 100 clients with different ratio of adversaries up to 80%. We use 50 rounds and yeah, that's it. Of course, we use Flower to do our experiments. So yeah, first of all, we measure the precision and the recall in detecting malicious models of both FL detector and Flanders when the ratio of adversaries is 80%. Clearly, our method works better than FL detector because it is not designed to work on 80% of adversaries. But however, even when we lower the ratio of adversaries, we still go better. But I have some tables on the backup slides if you want to see the results on 20 and 60%. Anyway, on the second table, you see how this has effects on the raw accuracy of the global model, where basically FL detector has the same performance of Fed average, while we remain robust because all malicious clients are filtered out by Flanders. Yeah, so then since Flanders can work with any classical aggregation algorithm, we pair it with all of them to see how much is the improvement of the global model accuracy. And the results are in line with the first table you saw before. So Flanders always improve the performance of plain aggregation functions. And also it enabled them to work when the number of malicious clients is more than 50%. So now we also added an adaptive attack for Flanders, as I was saying. We designed two versions. The first one is the non-omniscient attack, where the attacker has no knowledge of the parameters selected by the server. Didn't say it before, but to keep the metrics small, the theta t that you saw before, we have to analyze only a portion of the model parameters. Otherwise, the computational complexity explodes. And so I was saying the second version is the omniscient attack, where the adversary knows the parameters. And so in essence, we embed the attacker with a MAR model that used to generate its local model, which should be close enough to the estimation of the server, so that it can somehow poison the global model by breaching through the defense. And so here you see the non-omniscient scenario. So in this case, the attacker selects the last layer to poison. But as you see, it seems to not have almost any effect, even for Fed average. And so instead, in the second scenario, this is more punishing for Flanders. You see that even even for Fed average, even Fed average is better than all other aggregations in most cases. And I suppose this is because averaging all clients instead of a subset mitigates the effect of the attack, given that the perturbation is small. Otherwise, it couldn't make its way to the aggregation level. And you also see that the experiments with Flanders have always lower performance than their counterparts without it. And the reason behind this is that the malicious models are so close to the estimation of MAR on the defense side that Flanders selects all of them, or at least more frequently than multigram. The good news is that the effect of this attack is not disruptive, but you see here that there is a clear trade-off between the effectiveness and the stealthiness to take into account. But I think this is a good starting point for future research directions. And so let's discuss a couple of limitations. First, the estimation phase is quite expensive. So as I already mentioned before, we have to select a subset of parameters to keep the matrices small and thus contain the computational expenses. And second, Flanders needs to keep and manage a history of parameters sent to each client to make accurate estimations. And this is a problem in cross-device settings because not all clients participate at each round. And thus we have some kind of holes in the histories. We mitigate this by filling the hole with the current global model, but this is not optimal because clients can have a very skewed parameter distribution with respect to the global model. However, we don't have a better solution for this issue right now. This also can be another future directions. And so speaking of which, there are a number of works that, according to me, are interesting to explore. The first one is to look at the average anomaly scores of legitimate clients and malicious ones. And by looking at the delta between the two, we have a metric for exploring different hyperparameters for Flanders, such as, for example, the training size, the training set size, which is also the size of the sliding window, right? And or we can test the use of different distance functions, such as the cosine similarity, or use different prediction techniques than MAR, because now we set it as an optimization task, but it can be swapped with a learning algorithm that can be harder to train, but faster at inference time. And also, this analysis can also help to choose what is the best optimization algorithm to employ locally on clients, because the one that has the smallest anomaly score is more predictable, thus it's easier to classify as legitimate. And next, it can be interesting to integrate Flanders into an asynchronous setting. In this scenario, the server should only estimate vectors instead of matrices because models don't arrive all at once. And this is kind of cheaper in some ways. So you predict vectors, but you predict them more often. So at least for the memory requirement becomes lower, I believe. And finally, I think it is quite easy to adapt this implementation into a decentralized federated learning scenario from the less decentralized one, where you have a number of different servers that care about a subset of clients, to the extreme case where every client is a server itself and communicate with its peers. However, in this setting, the history can be quite tricky to manage if the network is highly dynamic. We just fall into the same setting, the same problem of the cross-device settings, right? So just be aware of this. And okay, so this is the end. Thanks a lot for listening, and I hope that this was interesting to you. If you have any question, I'm here.
Thank you. Thanks so much. Very cool. Very cool work. I'll take a look on Slack. If anyone is online and wants to ask a live question, just you can raise your hand or post your question in the chat. I'll take a look on Slack as well. But while I'm taking a look to see, or maybe where people are thinking about what they want to ask, I was going to just ask a kind of silly question, which was, where did you get the name from with Flanders? Was there any particular inspiration there?
This is an invention of my advisor.
Ah, I
Uh,
see.
he is a fan of The Simpsons, no?
Oh, yes. Yes. So like
Yeah,
Ned Flanders from The Simpsons.
exactly. Though, so it like kind of adjusted this in a way that it is also an acronym for our work that I always forget, but it's written in the introduction of the paper. And yes, also Flanders is like a field of flowers in the Netherlands, or
Yeah.
I don't, yeah. So it kind of falls into the same topic of the framework of flower.
Oh, I see. Oh, that's very cool. It's a cool name. I didn't see that connection. Um, Dylan's got his hand up, so feel free to like unmute and
Yeah, hi guys. Great presentation, Eduardo. I've got a
Thank
bit
you.
of kind of broad, general question just on poisoning as a whole. I was just wondering, has anyone ever really observed this in the wild? Because I always read about poisoning attacks, and I just wonder, how much of this is a bit of a, theoretical um, risk that we think federated learning could pose versus, most of the applications and settings I see are, like things like hospitals working together, or in our case, insurance companies. I suppose maybe they could do there. Um, I'm just never quite certain, do you think federated learning could reasonably lead to, malicious agents poisoning each other?
So in a practical setting, I think that yes, there is a. You are asking for a practical setting, right? So you mean practically if there is really a risk of um, the server being attacked.
Yes. Yeah, I guess. Yeah. Yeah, I was thinking, in like, yeah, some
Okay, yeah.
classic examples like hospital networks. I guess the hospitals probably wouldn't, but yeah, you could get an external malicious agent that would try and
Yeah, so I think the hospital setting is actually a good example because uh, I think you know that hospitals are always targets of hacker attacks, and they usually also realize successful attacks. And I think this is quite uh, quite important to address. And also another example is uh, I always think about this. So you have like a network where of clients that where everyone can join, and so you don't have really the control of who joins and who is who. You don't know the identities. So if you are a company that just want to I don't know, want to employ federated learning because it wants to um, like uh, learn a globally shared model without breaking the privacy of their clients, and you cannot control who joins. So you you have to take into account that probably some malicious actor can like make fake clients and yeah, try to ruin your business or
like, I guess
your company.
yeah.
I guess pointing out that like in cross-device settings, it's far more sort of plausible because you can have many
Yes,
devices that could be under controlled if they're Android phones. But I suppose there's other settings, such as the one Dylan was mentioning, that are probably far less likely to experience this sort of attack. Um, Given that if it's a network of hospitals, there's already quite a big trust established between them. Um, but it all depends on I think, what risk factors are really important for you to protect against, because perhaps you also want to ensure that a rogue actor within an insurance network perhaps can't. But maybe you want to make sure that it's impossible for it to be done, even if it is not very likely in general. Anyway, I guess it's certainly an interesting question. One question I had was, how would your work relate to LLMs in the sense of many, there's quite a bit of discussion about poisoning in those sorts of models. And I wonder if there is some sort of parallel between the degradation of data when that might occur if you're just scraping web data, you're not sure where it comes from. The data quality could be quite low, and then perhaps there could be similar, almost poisoning-like effects in training your model. If you're just kind of just gathering data without looking much into what's there. So I guess those are two kind of interrelated questions. But how would your work relate to LLMs, if at all, and any thoughts on these sort of directions?
Yeah, of course you can employ Flanders on an LLM. Yeah, that's perfectly possible, but there is a big problem, that is the computational expenses. So LLMs have billions of parameters, and so this matrix here, this one, theta t, will have basically billions of rows, and so you need a very big, a lot of computing power. Otherwise, as we do now, we randomly select some parameters to make the matrix smaller, but this is an approximation. Now, I also know some words that make a tie between the parameters that are most important to a certain input, so one maybe can employ this technique to select the most important parameters and use only them. But I think also this is quite expensive, but yeah, it's I think a good way to continue the research and test it on LLMs. What was the second part of the question?
Oh, just I suppose it was a bit loose. I was just thinking that at some point poisoning is related to data quality.
Yeah, sure.
And so I guess poisoning is more of a deliberate act, maybe computationally, algorithmically driven. But then on the same continuum, you could have just when your data quality is low, it affecting your model as well. And what are your thoughts? Do you have any thoughts in that direction? Do you think that we could adapt some of these poisoning protections in these cases where you're just kind of sucking in lots of data, but it's of variable quality, and you want to filter some of them out? Or I don't know. Any thoughts in this direction? Feel free to say it's not appropriate. It's that the two things do not align.
No. It's this is the problem of the quality of data and also the data distribution among clients that can be confused with malicious attempts to attack the model. It's something that I thought about it, and I also read in the literature. And so I think that Flanders can help in some way, because by looking at the history of the evolution of the model parameters, I mean, it can be, so let's take CRAM, for example, right? So CRAM doesn't look at the history. It just look at the, let's simplify it, at the distance between each model. So a model that is that has been learned on trained on a bad data set, it's very far from the others models that instead are trained on quality data. And this can be confused by a malicious client. Flanders instead, by employing this history of temporal evolution of the models, it can somehow distinguish between a very like that at some point I imagine that a model poisoning attack at some point just make a very different prediction about a very different update about the last time that the server saw the model.
For sure.
Instead, when the data quality is very bad on a certain client, it is always the word it's always coherent with itself along the history, right?
I see. Yeah, I see.
Yeah, I explained it in a very bad way, but I hope this is clear.
No. I understand what you're getting at, particularly about the sort of one opportunity you think is related to the sort of similarity of the data of the client, not sort of being kind of consistent with one sample to the next.
Yeah, exactly. Yes.
Yeah.
Yeah.
Well, that's very good. Very great discussion. We're actually running a pretty low on time, so I better wrap things up. Thank you so much for the talk here.